Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today, we'll be working on Unit 6, Lesson number 4 on complete factoring. So complete factoring is something that we've introduced in a previous lesson, but now we have most of the major techniques that we'll use in complete factoring. This lesson will also give us a little bit of a view on how we can use the idea of complete factoring to actually make factoring trinomials easier. But let's recall first what complete factoring is. Or not. Actually, first, let's do some products. It says write each of the following in their simplest form. The last two should take little time to do. Now, what do we really have here in terms of products? What we've got is we've got the product of three things. And of course, whenever you multiply three things together, well, you got to multiply two things together first, and then multiply by the third thing. And it doesn't matter what order you do them in, because multiplication is both commutative and associative, giving us permission to do them however we want. So in this first problem, what I'm going to do is I'm not going to do anything with the 2, and I'm going to actually multiply all of this stuff out, right? So I've got x times x, which is x squared. I've got 4 times x, which is 4x. I've got 7 times x, which is 7x. And I've got 4 times 7, which is 28. All right, I'm just going to keep writing this 2 down. 7x and 4x is 11x plus 28. And now that I've multiplied those two binomials together, I can now distribute the 2, and I'll get 2x squared plus 11. Oh, let's try that again. 2x squared plus 22x plus, what would that be? 56, I think. All right. Now, I'm going to actually skip over and do C, because then I'm going to want you to loop back and do B and D. So I know this is a little bit strange, but I said the last two should take little time to do. And the reason they should take very little time to do is that when I see x minus 5 times x plus 5, I can go through all of this if I want. But if I recognize that they're those conjugate pairs, then I should recognize that I'm going to simply get x squared minus 25 out of them. When I then distribute the 3, it makes it very fast, 3x squared minus 25. So D is very similar to that. What I'd like you to do now is pause the video and go through both B and D, and then we'll take a look at the answers. Okay, let's go through them. Again, I'm gonna hold out on that GCF until right at the end, give myself a little bit of room here. So I'm gonna keep that 5 hanging out there. And then what will we have? 2x squared minus 5x plus 6x minus 15. Again, just having the 5 hang out. 2x squared plus x minus 15. Now I can distribute that 5. Take my time. I'll get 10x squared plus 5x minus 75. Likewise, this one should be pretty easy because we've got another conjugate pair right here. When we multiply those together, we'll get 9x squared minus 4. And then I can distribute through by the 4x. Now watch out, I'm distributing a 4x, so 4 times 9 is 36. But x times x squared will give me that x cubed. 4 times 4 is 16. And the x comes along for the ride. All right. Now today, with complete factoring, we're going to go in the opposite direction. We're going to want to start with the things that are circled and move backwards until we get the original product. Okay? So pause the video now and write down anything you need to. Okay, I'm going to clear out the text and let's move on. Let's talk about complete factoring. Now we can talk about complete factoring. Complete factoring means to factor until there's no further types of factoring are possible. Nothing else is possible, right? So to really kind of hammer this point home, let's take a look at our first factoring exercise. Now, here we've got this trinomial, 2x squared minus 4x minus 6, and it says verify that both of the following products are correct factorizations of this trinomial. All right? Well, let's just first see if they're reasonable. 2x times x is 2x squared. Negative 6 times 1 is negative 6, so that's all good. Let's just do what we did in the last lesson. Let's see if that inner and that outer sum to give me that middle term. And there it is, that negative 4x. Great. Let's check this one. So that's a correct factorization. Let's check this one. Well, 2x times x is 2x squared. 2 times negative 3 is negative 6. Here I'd get a positive 2x. Here I'd get a negative 6x. And when I sum those, I'll get negative 4x. Correct. So there's 2 correct answers. But letter B asks the most important question, which is why are neither of these completely factored? Pause the video now and think about that for a moment. Okay, let's talk about it. Well, let's take a look at this one. 2x minus 6 times x plus 1. The reason that this one is not completely factored is that there's a GCF of 2 in that parentheses. Same deal on the other one, right? When I have 2x plus 2 and x minus 3, the reason this isn't completely factored is, again, there's a GCF of 2 in that parentheses. Now letter C says write each of these in completely factored form by factoring out the GCF of each unfactored binomial. Sorry about the wording there, but sometimes you got to do what you got to do. All right. So, well, let's take this one. 2x minus 6 times x plus 1. All right. I can further factor that by taking a 2 out of this. Now, what would that be? That would be 2 times x minus 3. That x plus 1 just is what it is. It just stays like that. So this is very similar to a factor tree, right? You remember those factor trees? How I'd break it down like this, but then this one would break into that. All right, same deal. You know, on this one, 2x plus 2 times x minus 3. Here, I'm going to take a look at this one, factor a 2 out. That'll leave me with x plus 1, and then that x minus 3. Now, what's cool is letter D. What is true of both complete factorizations you found in part C? They are the same, right? Now, they may look a little bit different, but that's only because the order of factors are different, right? And what this really goes to show is it doesn't particularly matter when you completely factor the order in which you do it. You just have to keep breaking things apart, right? And that's no different than, say, when we have some number like 28 and we want to completely factor it. We could start it as 2 times 14. The 2 is completely factored, but the 14 would have to be broken into 2 times 7. And therefore, we'd have 2 times 2 times 7. That's kind of what we did here, right? Likewise, you know, we could have 28 and break it into a 4 times 7. And that means the 7's fine, but then we'd have to break the 4 into 2 times 2, and we would still get exactly the same answer. So what works for integers also tends to work for polynomials when it comes to factoring, and a lot of other things. All right, pause the video now, write down what you need to, and then let's do some complete factoring. All right, let's clear it out. Now, although it doesn't really matter the order in which you completely factor, what is helpful is if you look to factor a GCF out first. So again, you don't have to, but it's very helpful, very helpful to factor out a GCF first. All right, so let's take a look at this guy, right? When I look at the 4, the 12, and the 40, I can factor a 4 out of each one of those. And what I'll get is x squared plus 3x minus 10. Now, you can't lose this 4. Some people just drop it. It just vanishes. And that's just strange. I mean, it is an equal factor to the x squared plus 3x minus 10, right? So we should keep that 4. What we now have to do is we have to guess and check on that trinomial. But this is one of the easy ones because the leading coefficient now is 1. So I have an x and an x. I think it's going to be 5 and 2, and I think it's going to be positive 5 and negative 2. Now again, although I've written the 4, I'm ignoring it as I check this. Negative 2x, positive 5x is positive 3x, and again, I'm looking at this thing. And because that all checks, I can say that this is a correct complete factorization. Now, I think we'll even have an easier time with the next one because we've already done one like this, right? 6x squared minus 24, both the 6 and the 24 have a common factor of 6. When I factor it out, what I'm left with inside is x squared minus 4. This is now that difference of perfect squares, right? It factors as x minus 2 times x plus 2. The beauty of the difference of perfect squares is that you don't really need to check it. You can check it, but unlike trinomial factoring, where checking's the whole method, that's everything, here you don't have to. Now, C and D are very similar to A and B. So what I'd like you to do, pause the video now, and then work on completely factoring those two. All right, let's work through it. Let me try to find a little bit of room, maybe down here for this one, below this. So I look at the 2, the 20, the 50. This isn't too tough. We factor out a 2. And we'll end up having x squared plus 10x plus 25. All right, again, don't lose that 2, but now we're going to do a little guess and check on trinomials, x and x. This one ends up being kind of cool because it has 2 identical binomial factors. And again, real quick check, 5x and 5x gives me 10x. It's all good. That is a complete factorization. Let's take a look at letter D. All right, if I look at the 75 and the 3, I can factor out a 3 from both, and I'll be left with 25 minus x squared. That is, again, the difference of perfect squares, and it can be factored as 5 minus x and 5 plus x. Make sure that you have 3 times 5 minus x, 5 plus x. Make sure you do not have the following. This would be incorrect. All right, lots of students always want to put the variable first, but that actually wouldn't check. If you multiplied it all out, you wouldn't get 75 minus 3x squared. You'd get 3x squared minus 75. Subtraction is not commutative, so that wouldn't be correct. All right, we'll pause the video now before we go on to the back side of the sheet. Write down anything you need to. All right, I'm going to clear out the text. It's gone. Let's do some that are a bit more challenging. All right, so these are 2 trinomials that are going to be a little bit harder in terms of the guessing and checking. So let's do the first one together, okay? And then we'll have you work on the second one on your own. So I'm going to look at this one, all right, and I'm going to look at those 3 terms, and I can see that a 5 will divide into each one of them. Now, when I factor that 5 out, I'll be left with a 2x squared, and 11x, and a 25. Oh, no, not a 25. That's what happens when I try to do the math too much in my head. How about a 21? Yeah, I like that a little bit better. Now again, the only thing that makes this particularly difficult, more difficult than the last ones, is that leading coefficient is not 1 anymore. So now I have to kind of set back and go, okay, I'll have a 2x there and an x there. And then I have to look at the 21 and I have to think, well, I got 3 and 7, 1 and 21. It's probably this one, but one's got to be positive and one's got to be negative. So, let me put the negative 7 there. Let me put the positive 3 there and check. Let's see, we got a 3x and a negative 14x, and those will combine to be negative 11x. But I have positive 11x. Now, when something like that happens, what that tells me is that I really just got those 2 wrong in terms of plus and minus. I think what I really want is a positive there and a negative there. That'll turn this to negative, this to positive, and this to positive, and it'll all check. All right, why don't you give yourself a test now, pause the video, and try to work out letter B. All right, let's take a look. 12, 57, and 15. I'll go back to blue. I think a 3 goes into each of those. Let's see, what would that be? 4x squared. Now here I might have to have a calculator, do 57 divided by 3. I don't know, it's kind of up to you. I'd get 19x, then deal with the 15, that'd be negative 5. Now this one's even harder because the leading coefficient is not only not 1, it's not even prime. So it's tricky. Do I go with 4x and 1x? Do I go with 2x and 2x? Well, just because I've worked on this problem quite a bit, I know this is the correct factorization. But let's take a look at why, right? Negative 1 times x, well, that'll be negative 1x. Here I'll have positive 20x, and when I sum them together, I'll get that 19x. Remember, I'm looking at this, not that one. So there is our complete factorization. Okay, so completely factoring something is, it's longer than what we've been doing, but really all it means is that we first try to take a GCF out, if even possible. We're going to see some very soon that have no GCF, and then moving on to either the difference of perfect squares or GCF, greatest common factor, or sorry, difference of perfect squares or trinomial factoring. Anyway, pause the video now, write down anything you need to, then we're going to clear out the text. All right, let's do it. Let's go on. Now, the last thing that we're going to do is introduce even more intelligent guessing. And this can help you in terms of being able to factor trinomials effectively and, important, efficiently. So let's walk through this one. Consider the trinomial 4x squared plus 5x minus 6. Does this trinomial have a GCF that can be factored out? Think about this for a moment. Okay, and the answer is no. All right, if I look at the 4, the 5, and the 6, there is no common factor amongst all three of them besides the number 1. Now let's take a look at letter B. It says the two products listed below are not reasonable guesses for the factorization of this trinomial. Why? Now, before we go there, let me just say they're not terrible, right? 2x is 4x squared, negative 3, positive 2 is negative 6. 4x, 4x squared, positive 6, negative 1, negative 6. So they seem like they're reasonable. But think about why these would not be reasonable guesses, why I shouldn't even guess them. All right, well, here's why. This has a GCF of 2, and this one has a GCF of 2. But the original trinomial didn't have a GCF. And a GCF is not going to suddenly appear when there wasn't one to begin with. The factors are the factors. When you factor a number or you factor a polynomial, it doesn't matter the order in which you factor. If there's a greatest common factor that can be taken out, that should be able to be taken out right at the beginning. So if it can't be, then you have no GCF. So let's take a look at letter C. It said, could a binomial of the form 2x minus a times 2x plus b, where a and b are divisors of 6, be a correct guess for the factorization of this trinomial? Why or why not? So in other words, is there any possibility that this thing has the leading 2 of 2x and 2x? Think about this for a minute. All right. Well, the answer is no. Okay, and the reason isn't the 2x and the 2x, it's all about the 6. You see the 6 here can be factored as 1 times 6 or 2 times 3. And if you've got something like this, and let's say you went with the 1 and the 6, I'm not going to even put pluses and minuses, there'd be a GCF, right? Or if I went with 2 and 3, there'd be a GCF. So those shouldn't even be attempted. I shouldn't even write them down, which is awesome. Because even though that 4x squared is annoying, I know it's got to look like this. It's got to. Now think about the 6. The 6 breaks into 1 and 6 and 2 and 3. All right? But whatever we do, we're not going to put one of the evens here. So let's say we try this, right? Now, we can automatically know that's not going to be right because we're going to have 1x and 24x. One's going to be positive, one's going to be negative, but they're not going to combine to be 5x. So that one's out with a really small eraser. Okay, so it's not the 1 and the 6. All right, so it's got to be the 2 and the 3. And yet if it's the 2 and the 3, the 2 can't go there. Otherwise, there'd be a GCF, right? So it's amazing how many guesses we can eliminate. Now we have it, right? Because now we have a 3x and an 8x. And I need to have a positive 5x, so that's got to be negative 3. That's got to be positive 8. That has to be our correct factorization. So knowing that a trinomial does not have a GCF leads us to create guesses where the binomials that we write down also don't have GCFs. And that can be very, very helpful when you're factoring a trinomial. All right, let me pause there because I really want you to think about this exercise, and then we'll clear out the text. Okay, clearing it out. Let's do a last problem. Use the intelligent factoring tip developed in exercise number 5 to factor each of the following trinomials. Note that neither has a GCF to begin. Okay, so let's talk about this intelligent way of factoring. All right, let's take a look at this one. Thank you for clearing the page. All right, we have 6x squared minus 13x plus 6. Well, the 6x squared will either be a 3 times 2 or a 1 times 6. Let's go with 3 times 2. All right, let's go with 3x and let's go with 2x. Same thing is true here. This is either 1 times 6 or 3 times 2, and they've both got to be negative. Now, if it's 3 times 2, well, then the 2 would have to go here, and the 3 would have to go here, because otherwise we'd have GCFs in both of them, and that would be a problem. They'd both have to be negative. So let's see. Here I'll have negative 4x, here I'll have negative 9x, and I'll get negative 13x, and that's right. Look at how quickly I got to the right one. All right, now maybe I got lucky because I guessed that 3x and that 2x first. But the plain fact is I knew not to put the 3 with the 3 and the 2 with the 2. Otherwise, there'd be GCFs. You take a shot at letter B. Pause the video now. Okay, let's talk about letter B. Boy, 12 is a tough one. 12 is about as bad as you get because it's 1 times 12, 2 times 6, 3 times 4. 8's not that great either. 1 times 8, 2 times 4. All right. That's it. So let's start. Okay, let me actually start with one that probably isn't going to be right, but hey, why not? Let's go with 12x and 1x. Now, I can't go with the 2 and the 4, because if I go with either a 2 or a 4, whichever one gets paired up with the 12x will have a GCF of 2, and this thing has no GCF. So if the 12 and the 1 are right, then it's got to be 1 and 8, and it's got to be in that order. I can't put the 8 with the 12, otherwise there'd be a GCF of 4. All right, well, let's take a look at these. 8 times 12 is awfully big, but it's 96x, and 1 times x is 1x. And there's no way we're going to rearrange those to get 29. 96 minus 1, 96 plus 1, it's not going to happen, right? But that means that one's out. Okay, let's try the 2 and the 6. Let's try 2x and 6x. Now again, the 2 and the 4 are out because both of them are even. I can't pair either of them here. So if this is going to work, I'm going to have to, oh, the 1 and the 8 aren't going to work either, right? Because if I do this, there's a GCF. And if I do this, there's a GCF. So actually, that's done. All right, moving right along. Oh, it's got to be the 3 and the 4. So let's do 3x and 4x. Okay. Again, it can't be the 2 and the 4, because if I do 2 and 4 and I pair either one of them with the 4x, there's going to be a GCF. So it's got to be the 1 and the 8. The 8's got to go here because it can't go here. Otherwise, it's a GCF. The 1's got to go there. Let's take a look at what we have. We have 32x and we have 3x. And that will combine to be a positive 29 as long as that's negative and that's positive. So it all works out. And there it is. That's it. All right, pause the video. Think about what we did here. All right, I'm going to clear out the text. Okay, So in today's lesson, we reviewed the idea of complete factoring. And again, it's very simple. Step 1, look for a GCF, factor it out if you can. Step 2, look at what remains. If it's a trinomial, use some guess and check. If it's a binomial, consider the difference of perfect squares. All right. And that's basically it. Now, one of the things that complete factoring led us to deduce, though, was an intelligent guessing and checking tip on trinomials, which was simple. If a trinomial doesn't have a GCF, then neither of the binomials that are its factors can have GCFs either. It's pretty much that simple. All right. Well, thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.